Welcome back. Last lecture, we built the foundation upon cryptography, and we touched upon the hard math that it requires. And we talked about how the one piece that stays private is a key. Today we're going to go a bit deeper onto that key subject. What is it really? Where do the two big families of cryptography come from? And then we're going to talk about randomness. If you get randomness wrong, your entire model becomes useless. So it's very important that we talk about it. So let's start simple. What is a key? A cryptographic key is really just a big number, and that's it. A 256-bit key is a 256-bit random number. The algorithm is a public machine everyone can see. The key is the secret setting that makes your encryption yours and no one else's. Same algorithm, different key. A completely different result. And because the whole security depends on that key being unpredictable, where the key comes from matters enormously. This is why we'll spend half this lecture on randomness. But first, let's talk about the main two families. So there are fundamentally two different ways to use keys, and almost everything in cryptography is one or the other. The first is symmetric. With symmetric encryption, the same single key both locks and unlocks the data. Think of it as like a regular house key where you use to open it and close it. You use to open the door and you use to close the door. AES, the encryption standard we keep on mentioning, is symmetric. Because it's symmetric, it's very fast, very efficient, and it's what protects the bulk of real data. But it has one obvious problem, and that problem is the whole reason why the second family exists. The problem is sharing. If I and you both need the same secret key to talk secretly and securely, how do I make sure that key gets to you in the first place? I can't just email it, because if I email it, any network can grab it, and now our secret becomes public. This is called the key distribution problem, and for a long time, this was a genuine headache. You need a secure channel to share the key, but the whole point was you don't have a secure channel yet. So the solution was the second family, asymmetric cryptography. Asymmetric encryption uses two different keys that are mathematically linked, a public key and a private key. Here's a mental model. Imagine a mailbox with a slot. Anyone can drop a letter into the slot. That's a public key, and you can hand it out to the entire world. But you have the key to open the box and read what's inside. That's a private key, and it never leaves your hand. So anyone can encrypt the message using your public key, but only you can decrypt it. This quietly solves the distribution problem. Now, here's the thing that ties both families together and decides whether each one actually works. Randomness. Every key is supposed to be random, but it's not just the keys. We talked about a bit earlier in lectures, but salts are also supposed to be random, and they protect passwords. Session tokens are also supposed to be random. A lot of things in the world that are supposed to be private need to have a random element, because all of them depend on being unpredictable. What does randomness really mean in this context? You can think of it as unpredictability or entropy. High entropy means the attacker has little to no way to guess the value. Every possibility is equally likely, while low entropy means there's a pattern, a shortcut, or a small set of likely answers. And this is the trap. Something can look random to the human but can be completely predictable to the computer. And that's a lot of problems we have today. If I generate a random key, but I don't do it in a way an attacker can reproduce, then it doesn't matter if the key is 256-bit long. They don't have to try every possibility. They just have to repeat what I did. This is the exact difference between two kinds of random number generators, and confusing them could be a real vulnerability. A regular random function, the kind you use to shuffle a playlist like math.random in JavaScript, is fast but predictable. It's not built to resist an attacker, and often you can find out its future outputs from a few past ones. For anything security related, you need a CSPRNG. A cryptographic tool a cryptographically secure random number generator. Those are specifically designed so that even if an attacker sees a stream of outputs, they can't predict the next one. And the rule is simple. You don't want to use a regular number generator because of the fact that it's predictable. The computer has a bias. You want to use something that's truly random to generate keys, tokens, or anything secret. Let me show you how badly this can go wrong, because it's not really a hypothetical. This has actually happened before. In 2008, there was a bug in a version of OpenSSL shipped with Debian and Ubuntu. A developer tried to clean up the code and removed a line that fed unpredictability into a random number generator. It looked harmless at the time, but that one change completely collapsed the entropy. Instead of billions upon billions of possible keys, the system can now generate only 32,000 of them. The algorithm was completely fine, but the key generated on those systems for almost 2 years were guessable, because the randomness feeding it had been gutted. Now I want you to sit with that for a second, because it's a whole lesson. Encryption can be perfect, AES, RSA, all of that, untouched. And yet thousands of systems are wide open, not because of the fact that the math broke, but because the random numbers weren't random. An attacker didn't need to break the cipher. They just needed to generate the same tiny set of keys and try them. This is what I meant when I said randomness is the most critical part. It's invisible and it's easy to get wrong, but when it fails, everything can go down. There is a close cousin to bad randomness, and maybe it's one of the most common mistakes of all. It's called hard-coded secrets. This is when a key or password or an API token is written directly into the source code. It feels convenient at the time, it works in testing, and when the code gets committed to the repository, maybe even a public one, it's fine for a while. But the secret is just sitting there for anyone who looks into it. Imagine you have your own Git, right? And you have it private for a while. You maybe forget to add the environment file to the git ignore, and you maybe put an API key in there. And you're going about your work, and eventually you're ready to publish it, and you're ready to maybe make the repo public. But you forget to private the .environment folder. So when you make it public, everyone can see your environment folder and everyone can see your API keys, which actually has happened a few times, and it's a huge problem for you. It's a very silly mistake, but it happens all the time. And that's one of the main issues that we might fall into. In fact, there's actually a huge community that scans public code for accidentally committed keys, and that's an entire category for an attack, because people do this constantly. It's a very prevalent issue that you guys should not be making. So where should secrets actually belong? It shouldn't be in the code. It shouldn't be in the front end at all, because anything shipped to the browser or an app can be read by a user. So a secret there is already exposed. Not in logs where they quietly pile up in plain text. Secrets belong in environmental variables, or better, a dedicated secret manager, or a system built to store and rotate and hand out secrets securely, separate from your code. The principle is simple. The code should know how to ask for a key, but should never contain the specific key itself. And let's put this into the lens of a tester, because all of this turns directly into things you check. Are keys and tokens generated with a crypto-secure random source, not a basic number random function? Is there a real entropy behind them, or can you predict them? Are there any secrets hard-coded in the source, sitting maybe in the front-end bundle, or maybe leaked in logs? Are secrets stored on a proper secret manager and rotated when people leave them or something exposed? You don't really need to break any math to find them, and that's the main point of it. A lot of the times, it's never the problem of math. You just need to know where to look. And with this, hopefully, now you do. So, quick recap. A key is just a big secret number. Symmetric uses one shared key and is fast, while asymmetric uses public and private pair and solves the problem of sharing. Underneath it all is randomness. And randomness is the ingredient that decides whether any of it actually protects you. This is why weak generators and exposed secrets causes real breaches, even when the algorithms are flawless. Let's move on to the next lecture then, if you guys get this.